Hello everyone, my name is Phann Raksmey. Today I would like to present about EM-PINN for the battery SOH. Actually, before we understand about EM-PINN, we need to know about what is PINN first. But don't worry, I will explain you detail about what is PINN. This paper is published in Energy Journals in 2026. This study proposed the EM-PINN model based on the EMs of the SEI layer growth. I will explain you more about SEI layer growth because SEI layer is the key idea in this paper as well. Now we talk about motivations. Why the battery SOH is hard to estimate. I will compare the three models: physics only model, data model, hybrid, or PNN models. For the physics only models are attractive because they are interpretable, but they are expensive and often too slow for online battery management or for online use. For data only models are flexible but sensitive to data volume and distribution shift. For hybrid or PNNs, promising if embedded physics is truly informative. So this paper starts from the practical questions. Can we model a real degradation mechanisms instead of the generic ritualizers? Can that mechanism improve stabilities when training data are limited? Can the model remain physically plausible while saying aggressive? Now I will explain you about the methods. We start from the feature extractions. In the data preprocessing, there are two scenarios. The first scenario is child process and the second scenario is the child process. That reminds us that SOH is not observed directly. It has to be inferred from the measurable signals collected during the operations. And now look at the features curves. There are examples of this derived features trajectory such as current means, current slopes, current standard deviation, and the current entropies. Now we explain about methods. So obviously the basics neural networks. We have the info feature connect to the hidden layers to predict the SOX. And to get the good prediction, we need to optimize the data loss. But why only data loss is not enough? Because as we know, the battery SOH should normally go down with the times or cycles, not go up, right? But a neural network trained only on the data can sometimes predict a small upward jump in SOH because of noise, limited then training data, overfitting. That those upward jump are usually not physically realistic. So we need to add this penalties whenever the predict SOH at the later time is higher than Earth's early times. So now we consider about our formula. We use ReLU. Change the color. So the ReLU function ReLU of x equal to max, right? Maximum. We use maximum function. Sorry, I write so bad because I don't have a pen. Zero and x. Okay, so we use the ReLU. The purpose is if SOH t plus 1 less than SOH, it means no penalties. It equal to 0 for our loss. But if SOH plus 1 greater than SOH, the loss is positive. It means we add this penalties. And the last one is about the physical loss. The physical loss is introduced to ensure that the predicted SOH degradation is physically meaningful and its time derivatives give the predicted decay rates. Okay, now we continue to the key idea in these papers. As we know, in the battery contains electrolytes. So when we charge the battery, the electrolyte from this cathode transfer to the anodes. That reason SEA layers grows because as we see when we charge our battery phone, our phone is hot, right? Because this SE layer it grow. So when the SE layer grows, it means our battery also down. Like mean when we charge or we use our battery many times, our battery get old, right? That's why we consider about the formulas, the derivatives of the SOH. We can see there's minus here, this minus, and we multiply by the derivative of the SEI because it related to the SEI layer growth. As I mentioned before, when SEI layer grows, it means SOH downs. So now we got the total of the loss function here. For the data, it is the loss function of the data. It fit the measures SOH values. This keep the model hostness to data. And for SOH lowers P6, this one is loss P6. The max the SOH decay rate implied by SE grows penalize non-monotronic SOH predictions. And alpha beta is the hyperparameter to control the loss function. And for this loss, ensure the PDEs, initial and the boundary conditions. Constrain the hidden signals to obey the governing equations. So to my read these papers, many papers say the P6 informs, but these papers earn the term because the P6 shape both target and the visible sets. Okay, so now let's see this our input and the benchmark for our data. So we experiment with this 3 datasets: HJTUs, MITs, HUSTs, and the author also analyze about the head mix. So some picture we can see the correlate consistently across data sets. Another set with the chart and the chart protocols. This is exactly why the robust physics bias matters. So the first thing in the data, the author checked the features, capacities, correlation before the choosing those imports. So now we can see the result on the XJTU dataset. It is our proposed model, EM-PINN. We can see it is the best one. Both cell 1, and cell 4. So now we check our result. We can interpret EM-PINN is the computes on the mean error and better on the variance. And that's matter because repeated trial stability is what make the method trust in the protocol. And the author also report a 0.7 lower overall MAPEs than the PNNs across both HJTU datasets. Okay, now we will talk about the robustness. We do experiment in total 9 experiments. Yearly prediction, we train on the earliest part of the lies, and we can see that the EM-PINN still beat the earlier PNNs. And for the ablations, we remove the electrochemicals, physics, and keep only data loss plus the irreversible decays. So we remove it to make sure that and Bruce our EM-PINN still work well with without the electronic course physics or not. So we can see the error increase. That's why it means the EM is very useful, right? Because when we remove, the average error increased by 34.6% in MAPEs and 28.9% in the OMSs. So the gain is not cosmetics. The physics prior is doing real works. Okay, now we see the results. Small sample perform hysteria punchlines. We can see our proposed model and another model like RNN, CNN, LSTM, and the PNNs. So both dataset, MIT dataset and HUST dataset, the result MAPEs with the only 10% of the data. We can see this our proposed model can get the best result both the data sets. And if we check on the HUT data set, at the 20% mean error is lower and EM-PINNs keep one of the smallest standard deviation. So after I finish review the papers, I have my own evaluations, what is strong and what is limited. So what we see as EI growth is directly converted into an SOH decay signals. That means the physics is explicit, not hand-wise. And the loss design is coherence, data fit plus mechanisms based supervision plus flexibility constraints. Experiments are broad enough to test accuracy, robustness, and small sample behaviors. And the last one, the repeated trial analysis is a real strength because it rewards stability, not lax. For the limitation, the mechanism is still narrows as its growth is important, but not the only aging pathways. The model still depend on the head graph feature rather than raw sequentially learnings, and the deployment costs uncertainty estimation and cross chemistry transfer are not deeply analyzed. Some tables in these papers suggest the variant but stronger uncertainty story would help. So I would rate this a strong and instructive papers because it showed how domain knowledge can shape the objectives functions, not just the narratives. So to conclude, the EM-PINN is compelling because it turns electrochemistries from these backgrounds knowledge into the target networks must satisfies. Better physical priors can improve not just accuracy but stabilities. The payout is strongest when the data are limited. This paper is valuable as major lessons beyond the batteries. But if I extend this work in the future, I would add multi mechanisms priors beyond as it grows. And the second sequence encoder that improve feature engineers. And the last one, uncertainty estimate for the deployment in BMS. Thank you for your attention.